We can now solve for the normal stresses and for the shear stress. That is the magic of the area stress function. So we differentiate twice with respect to y to get sigma x, and that leaves us with c4x squared plus d4xy plus e4y squared. But we just went through the trouble of expressing e4 in terms of a4 and c4. That was I just did on the previous page. So I'm going to pop that expression in for e4 into here. And notice now we have three constants. We have c4, d4, and a4. So this 3 is kind of important here. For sigma y, we differentiate twice with respect to x, and we get a4 x squared plus b4 xy plus c4. And I was going to say these are the same three constants, but they're not, because we have a b in here now. We didn't have a b in this one. And then tau xy, don't forget the minus sign. I always forget the minus sign. Partial x, partial y of phi. We get b minus b4 x squared over 2 minus 2c4 xy minus d4 y squared over 2. So we have c4, b4, a4. We got a lot of constants here. So let's start solving for some of these constants. And I will do the first version of this, and then we're going to ask you to do the second version of this. But once again, this is one of the highlights of the course, I think. It's a cantilever beam with a point load at the tip. The height of the cantilever beam is 2h. The width of it is t. But this is such an amazing problem. It's a problem filled with struggle, with drama, and a happy reunion at the end. What could be better than that? So this is like a Hollywood film, this little cantilever problem here. So we're going to do version 1 right now together, and then you will do version 2 for homework. So the first thing is to say, well, let's look at this cantilever beam and actually find phi. We haven't done that yet, but we know some behavior of phi. So phi must provide a sigma x that is a function of x and y. So I'd like you to start thinking about that. You could hit the pause button if you'd like. Why is sigma x a function of x and y? It's not a function of x squared or y squared in this problem, because sigma is mx m times y over I, and m is p times x. So it's only a function of x and y. Tau is a function of y squared and a constant. Now, I'd like you to find out, where did you get that from? So go ahead and hit the pause button and find, where did you see that tau was a function of y squared and a constant? And the answer is, after you unpause the button, that we actually worked on this expression before, and we derived it here. So we're targeting a tau that has a y squared and a constant. So hey, how about a fourth over 12 times x to the fourth, b4 over 6 x cubed? We just saw that, right? We just explored that one. So let's go ahead and try this. We just said that sigma x is here, c4 plus d4xy plus e4y squared. But I made that substitution in for the e4, so we're left with this expression here for the sigma x. Sigma y is given, and we have the tau xy. Okay, so all I did was I used this area stress function to get these sigmas, but I swapped in the e4 that I did before. So now some insights here is, and I already said it just a minute ago, is it a function of x squared and y squared? The answer is no, it's a function of x and y. So therefore, This is an engineering insight. There is no dependency on x squared, and there is no dependency on y squared. So C4 and A4 must be 0. The next insight is, what is sigma y here? What is sigma y in this problem? The answer is 0. So if A4 and C4 are 0, therefore B4 must be 0 for sigma y to be 0. So we're starting to eliminate some of these terms here. If C4, A4, and B4 are 0, then we're left with this. And is this good or bad? D4 times y squared over 2. And go ahead and hit the pause button. And the answer is this is not good, because tau is supposed to be a constant and then y squared. And we don't have enough oomph here. This is not big. So this beast here is going to win this battle unless we get a bigger sword to slay the beast.